Dear ladies and gentlemen, I'm Lorenzo Badini, a PhD candidate involved in a double degree doctorate between the University of Bologna and the Technical University of Munich, and I will present our ongoing research at the Chair of Timber Structures and Building Construction of Professor Stefan Winter. We will go through a brief introduction of the framework, followed by a presentation of the integrated system, a description of the main connections provided and their finite element modeling procedures, the seismic analysis performed with relative main results, an example of the design technological solution, and wrapping up with the main conclusions and possible further steps. Target of our retrofitting strategy are the reinforced concrete building stocks. Recent seismic events have demonstrated the vulnerabilities of these buildings typology when built without anti-seismic criteria or with outdated standards. The same category of building constructed from the 50s to the 90s is also affected by high level of energy demand, and when addressed could entail major benefits toward the reduction of CO2 emissions. In this framework, the European project Proget 1 was born in 2017 with the objectives of increasing the seismic performance of existing reinforced concrete structures by means of an external steel exoskeleton that supports a new envelope and a new technical system to guarantee increased energy efficiency, and providing at the same time additional space for the existing residential units, increasing the market value and possibly mitigating the construction costs. The research here presented is therefore focused in developing structural configurations that could improve the safety of this building and be directly connected to prefabricated components, able to guarantee the efficiency of the envelopes. Life cycle assessment results developed within the European project shown that the environmental impact of the steel exoskeleton represent the main contribution and should therefore be addressed investigating alternative and more eco-friendly solutions. The assigned feasibility case study is located in Brasov, Romania, and it is a 5-story homeless dormitory, built in 1972. During the development of the project, technical reports on energy and structural performance have pointed out respectivity needs for energy improvement and a quite satisfactory structural performance due to a superstructure made of precast reinforced concrete panels that resulted incompatible for the application of an external three-dimensional strengthening structure. For this reason, the developed timber base is meant to stand alone and independent from the existing case study, here shown, providing only an architectural and energy renovation. For research purpose, the cross-laminated timber extension has been investigated in structural collaboration with a virtual moment-resisting reinforced concrete case study. The structure is developed with similar morphology to the previous one, located in the same seismic zone and designed for vertical load only, in order to be characterized by certain level of vulnerability. The strategy of the integrated system provides vertical 20 cm thick cross-laminated timber walls made of birch, placed in continuity to the existing reinforced concrete frames and providing seismic strengthening. Within these walls, 16 cm thick CLT slabs made of spruce are provided to guarantee additional space for the existing units and creating a structure that looks like a bookshelf. In longitudinal direction, the CLT-based structure is kept independent from the reinforced concrete frames, and by means of post-tension and moment-resisting connection, lateral stiffness is provided with the additional advantage of architectural freedom for the facade. The integrated system is therefore composed by the mentioned timber-based external structure, by a new envelope applied on the existing facade for the balcony solution and on the external perimeter for the case that provide extension of the rooms. Then new architectural components as technical beam with integrated railings are provided for the balconies, while new pre-assembled facades are installed for extra room and or some space solution. Developing the structural solution, particular attention has been paid to the post-tensioning connection, the connection with the existing structure, and the base connectors. Mentioning only some points of the finite element modeling, the existing reinforced concrete structure is fixed at the foundation level with external restraints. presents diaphragm constraints at the floor levels, and the linear elements, such as column and beams, have concentrated displacement controlled nonlinear hinges representing combined flexural and axial loads and flexural loads. Then force-controlled nonlinear hinges accounts for shear failures. The CLT panels are realized with shell-layered elements that provide orthotropic materials implemented in the software for the birch and the spruce. Simplified numerical tests have been done and compared with end calculations to verify the behavior of the elements. And the reduction factor applied to the material has been used to include shear deformation for out-of-plane loads. The post-tensional connection between cross-laminated timber elements have been developed within the project, adapting the analytical model developed by Wanninger and Frange at the University of Zurich. It is based on the Winkler theory that sees multiple springs representing the soft vertical element on which the horizontal rigid beam is compressed and rotate. Three main phases are identified depending on the position of the neutral axis at the interface, and through equilibrium equations, it is possible to determine the behavior of the connection and the rotational stiffness. The adaptation of the analytical model has been proposed passing from column beam subassemblies made of glulam to CLT two-dimensional elements by means of a composite steel plate that allows to increase the contact interface, reducing the compression perpendicular to grain and maintain adequate rotation stiffness and strength for the connection. Once the behavior of the connection is determined for outer and inner joints, both for horizontal and vertical loads, multilinear springs are created and inserted in the finite element model at the edges of all the shell-layered elements. A value representing the linear stiffness is also provided for the linear analysis. As you can see from the graphs, the shear deformation is particularly relevant and proportional to the eccentricity calculated between the resultant forces at the interface of the vertical elements. At the foundation level, consolidated solutions were provided to reduce the number of variables. 12 angular brackets and 16 all-downs are provided on both sides of the walls, with direct reference to behavioral laws derived from literature, and implemented in multilinear springs inside the finite element model, considering shear and axial behavior for the angular brackets, and only the latter for all-downs. A small contribute is also imputed to friction for the nonlinear analysis. Relative linear stiffnesses are implemented for linear analysis with particular attention to all-downs and their nonlinear behavior. Regarding the connection with the existing structure, 20 12 mm diameter steel reinforcing bars are chemically fixed to the CLT walls and already mounted at the construction site. Steel plates that provide tolerances for relative vertical and longitudinal displacement are then anchored to the reinforced concrete existing elements. For realistic applications, particular attention must be paid on the forces applied on the existing members, and when necessary, a steel jacketing could be provided to avoid local worsening of the reinforced concrete columns. The behavioral law of the steel bars is then inserted with multilinear springs in the finite element modeling, representing the axial behavior of the connectors. To transmit compression, pieces of hardwood or other materials must be provided above and below the steel connectors, avoiding the instability of the bars. Linear dynamic analysis have been performed in order to verify all the new structural elements and to verify the interstory horizontal drifts. Then, to assess the seismic vulnerability, the exploitation of the exoskeleton, and to obtain Q factors, pushover analyses have been performed in the two main directions with both signs and considering two different horizontal loads distributions. While the seismic vulnerability has been proved with target displacement verifications, following the Eurocode 8, the exploitation of the exoskeleton is obtained as a ratio between the horizontal loads taken by the external structure on the total. As a result of the linear dynamic analysis, checks on the structural elements and all types of connectors have been done considering ultimate limit state, serviceability limit state, and seismic combinations as significant damage and damage limitation. The interstory drifts, as shown in the graphs above on the right, become satisfied in the project solution. The post-tensioning connections were also checked in terms of maximum rotation and moment, ensuring values on the perimeter failure of the crane compressed perpendicularly and considering also a 30% of losses in the tendon forces. Nonlinear static analysis resulted in the satisfaction of the target displacement demands, passing from a vulnerability of 62% to 100% of the design seismic loads, considering the weakest direction and the distribution of forces proportional to modular shapes. As can be seen from the lower graphs representing the equivalent single degree of freedom system, the project state capacity curve is characterized by a stiffer behavior and an increased displacement capacity with respect to the initial state. This increase in displacement capacity can be noted in this picture, where the collapsing steps of the pushover are identified and compared for the initial state and for the project state. It is possible to notice the passage from a typical deformed shape of a moment-resisting reinforced concrete structure with damages localized in the lower levels to a more distributed deformations typical of rocky motions that allows the existing building to withstand higher level of acceleration. Above, results on the exploitation demonstrates values that run from 17 to 38%, showing margin of improvements that could be obtained with more efficient base connectors. Finally, one of the three main architectural solutions is shown, the extra room, that is also the more elaborated. In all three cases, considering also balcony and some space, prefabricated components are designed to be quickly installed on the main structure. The balcony presents a technical L-shaped beam fixed to the end side of the horizontal cross-laminated timber slabs and provides integrated railings. The same beam is foreseen for the sun space, where window frames can be then directly installed behind the railings from the inside. In both these cases, the new insulation layer is provided on the existing facade. Different is the case that we can see in the picture of the extra room, where the insulating layer is applied on the external perimeter and it is integrated in pre-assembled wooden frameworks that has to be installed from the outside in the bookshelf slots. In all cases, conductivity values associated to external vertical partitions are kept below the actual limits for energy-efficient houses. Concluding, the integrated system hereby presented is numerically proved to ensure structural, energy, and architectural renovation by means of a unique strategy representing an eco-friendly alternative to the more consolidated steel structure. Inter-story drift verification passes from 80 to 110%, target displacement verification from 62 to 101. The exploitation of the structure, although, could be improved, changing the connection at the foundation level. For example, the use of post-tensioning connections for the walls could increase the stiffness of the strengthening system and reduce the amount of connectors. The architectural technological solutions are provided for three different possible extensions, guaranteeing energy efficiency for the existing building. Architectural issues encountered and to be mentioned are daylight reduction that could be addressed with some devices placed on the external windows, possible reduction of usable height due to a different structural slabs passing from concrete to timber-based elements, and most commonly possible legislative impediments related to the extension that could increase the existing volumes. Here a slide reporting the bibliography of the presentation, and with this I conclude. Thank you for the attention. Any question will be welcome.